So our third skill in this unit on intermolecular forces and phase changes actually has to do with defining those intermolecular forces, which we'll abbreviate IMFs. Okay, so just reviewing, we saw this slide in our first skill, the difference between intramolecular and intermolecular forces. So intramolecular forces are within molecules. So these are the bonds that hold the atoms together. They give rise to the molecular shape, properties like bond energy, aspects of chemical behavior. That's not what we're talking about in this skill. We're talking about intermolecular forces, these non-bonding interactions that are between molecules. These are what are important for influencing physical properties that we'll talk about in this skill. So just highlighting, these are the intramolecular forces, things like ionic bonds, covalent bonds, metallic bonds. We've learned about these before, but these are all things that are within a substance, not between molecules, but within. And so these are not what we're talking about when we talk about intermolecular forces. Intermolecular forces, or IMFs, there's 4 that I want you to know, and I want you to know them by name, their hierarchy, kind of which is the weakest up to the strongest, and then being able to identify them in molecules, maybe sometimes draw them. Okay, so we'll get to that in just a minute. Here's the 4, and I'm going to give them to you in the order from weakest to strongest. The first is London dispersion forces. All molecules have what we call dispersion forces. If you forget that London part in front of it, that's fine. Sometimes we abbreviate them LDFs. These dispersion forces everybody has. They are proportional to size and shape. That's really, really key. London dispersion forces are proportional to size and shape. The bigger the molecule, the more surface area interacts, the greater the dispersion forces. Next one are dipole-dipole forces. We see these in polar molecules. So in the next slide, I'm going to do a little review as to what a polar molecule is. The next is hydrogen bonding. This is a special kind of polar interaction where you have molecules that have 3 important atoms. If you forget what these atoms are, look at your best cheat sheet, your periodic table. They're the most electronegative atoms all the way up on the top: nitrogen, oxygen, fluorine. Okay, so you have to have a nitrogen, oxygen, or fluorine in order to have hydrogen bonding. Okay, we'll get into some more details of hydrogen bonding in just a little bit. We'll practice drawing hydrogen bonds in class. The last is ion dipole, or even just ionic interactions, anytime you have an ion. And I want you to think about these. Imagine these sort of being like magnets. When you think about something like dispersion forces, there's no charge on those magnets. Dipoles, there's like a little bit of a partial charge on that magnet. Hydrogen bonding is a special kind of magnet, and then ions are like a fully charged magnet, either positive or negative. So that can help you rationalize this hierarchy as well, knowing that these are the weakest, are dispersion forces, and then anything with an ion is going to be the strongest interaction. So you need to know these by name and the hierarchy. And then we also need to know how and where to find these. Okay, so let's talk again just about polar molecules. This is a review slide from last semester's Gen Chem 1 class. How do you know if something is a polar molecule? Well, remember, first we need to ask the question, are there polar bonds? So you need to ask the question, are there polar bonds? To answer the question, is it a polar bond, you have to ask, are there 2 atoms that are bonded to one another that are not the same and not carbon and hydrogen? So I'm going to say that again because it's not necessarily written here. If you are a bond where the 2 atoms that are bonded are not the same and they are not carbon and hydrogen, we're going to say yes to you being a polar bond. If you don't have those, you can't be a polar molecule. You have to have polar bonds in order to be a polar molecule. But not all polar bonds make polar molecules. Remember, we talked about you can cancel out some of those polar bonds if your molecular shape allows for those tug of wars to cancel one another out. So does the molecular shape allow you to cancel those polar bonds? If the answer is yes, then you can't be a polar molecule, right? So here's a couple of examples of polar bonds but not polar molecules. So go back and review that content if you need to before we move on to this, because we need to make sure that we're able to identify polar molecules. All right, so what am I going to need to do with all of this? We'll practice a lot in class. We've got lots of examples of this. You might need to be able to determine for one molecule, what are the intermolecular forces that are present? Maybe being able to draw them. Okay, so we'll practice drawing dipoles and hydrogen bonds in class. Maybe I've given you two molecules and you need to compare them and determine who has the greater intermolecular forces. Okay, you're basically going to be going through a checklist of that hierarchy: dispersion forces, dipole-dipole, hydrogen bonding, ionic interactions. Whoever has the most check marks or the strongest check marks is going to have the greater intermolecular forces. One more layer on this is, you know what, those intermolecular forces affect things like melting point, boiling point, and vapor pressure, which we've talked about already. I'm going to mention two new ones, viscosity and surface tension, on the next slide, but maybe I've given you two substances and you have to tell me who has the greater boiling point, right? Remember, a boiling point has to do with how much energy do I need to put in? How high does that temperature need to be before I've given those molecules enough energy that they can break free from their neighbor? The stronger the intermolecular forces, the higher the boiling point. But make sure you see exactly how I've worded the question, because the question might say, who has the lowest boiling point? That would be the weakest intermolecular forces. So you have to make sure you look at the question correctly. We'll practice a lot of these in class, and there's lots of questions that you'll see like that on your online quiz. All right, last slide here, thinking about surface tension and viscosity, two terms that you probably haven't heard of before, but they're related to intermolecular forces. So let's define surface tension, right? This is the energy that's required to increase the surface area of a liquid. Well, you can think of it sort of being like pudding skin, if you will, right? When you've got pudding and that skin sort of hardens, you can think of it as being hard to kind of punch through because those molecules are kind of networked with one another. That's not really what pudding skin is, but it's a good conceptual to help us understand. So the fact that those molecules are sort of glued to one another makes it hard to break that surface, okay? So the stronger the forces between the particles, the more intermolecular forces you have, the higher the surface tension, the more energy it's going to take to break that surface. Okay, so that's how we define surface tension. But again, we need to answer the question first about intermolecular forces. All right, viscosity, sciencey term, right? But you can think of it in terms of how syrupy is something, right? We've got just an example here with water, which has a low viscosity compared to oil, compared to honey, right? Viscosity has to do with how strong are the intermolecular forces between these molecules such that they resist their ability to flow past one another, okay? So in this case, low viscosity means lower intermolecular forces than we have in olive oil or honey here, okay? So again, we can think about viscosity in terms of intermolecular forces as well.